given this piece here, I need to bring this back up. Given this piece here, it would seem to me that the focal length from the objective to wherever it converges is a big part of this magnification ratio.
Mm-hmm.
If you want to make a scope smaller, then you have to fake it. Basically, you have to find a way. Mirrors are one way of doing this. But to me, looking at this prism design, the Schmid-Pichan, if I'm following the light, it's bouncing around. So in this relatively short amount of space here, you're actually faking like you've got more distance for it to travel before it comes back out the other end. So in an optic, you get your objective, and I borrowed this graphic here from TradeCon itself, is on their About History page. You can see the light path going in, hits this prism, and starts bouncing around till it pops back out. So have you basically faked the amount of focal length that you got at that point?
So the phrase crayon eater, is that specific to Marines?
Yes.
Or is it a common practice among the Air Force as well?
It is Marines. We like to eat dry erase markers.
All right. That's fair. As long as you don't sniff them, just swallow them whole. You're not faking anything. This is something called the folded optical path length. You're trying to fit a longer focal length optic into a shorter housing. And a very common way of doing this is by using reflective optics. So common lenses that we are all used to, they're called refractive optics, right? And what refraction means is that you have a lens element and light goes through it. Okay, that's refraction. Reflective optics, as the name suggests, is basically a bunch of surfaces that for one reason or another reflect light rather than allow light to transition through this air to glass or whatever material interface. Reflective optics can be mirrors or they can be prisms. The big reason people use prisms frequently for this is that you can take a piece of glass and you can angle its sides in such a way that you have something called total internal reflection. What total internal reflection means is that if you have a plane of glass and you have light coming straight on, it'll just going to mostly go through a little bit. It's going to get reflected, but mostly it's going to just go through, right? If you want to minimize reflections, you put on coatings, etc. You can put on a coating to make it reflective as well. Now, if you start light coming in at an angle, as you go to more and more extreme angle, at some point you will going to get to some sort of an angle where beyond that angle, all of the light that comes in just reflects. It does not actually penetrate the interface between air and glass. Well, slightly. There's something called evanescent waves, but that's not really critical here. And that is the exact phenomenon that prisms use. They position different surfaces of the prism that most of the reflections are total internal reflections. The light just bounces off. Okay, so it gets inside the prism. So first, look at where your light path is on the left. There's a straight line where light gets in. Mm-hmm. Just walk to the prism and stop. Flat interface here, light comes through the air to glass interface. Then it hits the first surface over there. Stop. Here, there is only total internal reflection. The angle beyond which you have total internal reflection depends on the indexes of refraction of the two materials, in this case, glass and air. Right, so you can calculate it by the ratio of those two indices. But in this case, you have mostly total internal reflection. Then you go down, bounce off again, then go up. Now you're going through a couple of air to glass interfaces again because you get into the second prism. Then you reflect again, go up to the top. There is a complex surface, and that's where the reticle sits in the prism. So this is the one part of the prism. Notice the angle here is a lot closer to the right angle compared to the surface on top. So here you do not have total internal reflection. This is the coated part of the prisms. You know how it's more common with binoculars to talk about prisms being silver coated or multi-dielectric coated, whatever. This is a reflective coating that makes light reflect. But with prismatic scopes, that's also where the reticle sits. That actually introduces a couple of problems. Mm-hmm. And then it goes off, down, hits another surface. Now the total internal reflection again. No coatings, just that interface between air and glass is what makes it reflect, and goes out toward the eyepiece.
Okay.
Is making some sort of sense?
Yes.
Excellent.
So the next picture, because you mentioned actually the thing. So I actually borrowed this. This is a.
Oh, there you go.
So this is a drawing again from Trigicon of this optic here, that I'm holding up, and really I lost the stream for a second. So if you can see it, so this is Trigicon TA110. So this is the LED version of the one on the graphic here, which is the TA11. But basically, this chart is the inside of this thing. So this is where I thought it was interesting. You did point out that the reticle does sit on top. Actually, let me pick a different orientation here.
And notice
so the reticle is sitting up here.
Yeah, see where there is a red thing where it says tritium lamp low light reticle magnification?
Yep.
Notice that the way Trigicon, and I like Trigicon graphics, Trigicon is occasionally a complicated company, but when they decide to put together a graphic, it's actually good. Notice that the lines look like they're converging over there. They're converging on this point where it says tritium lamp low light reticle illumination, and then diverging again when it bounces off, right?
Mm-hmm.
Right there. See the lines are kind of converging, then diverging again?
Right.
That little orange spot where it says tritium lamp, low light, reticle illumination, that's where the reticle is. That's the focal point. That is the focal point of both the objective and the eyepiece.
Okay.
And in this case, your magnification is the ratio of these focal lengths, or also the ratio of the field of view and apparent field of view.
Okay. Yeah. So the interesting thing is I was looking at this graphic, was I actually was tracing the orange and the black lines to exactly what you just said, which is they continue to get closer together, even though they're all bouncing around in this stuff. And you're right. I actually didn't catch the first time that they converge right at that reflective point and then become diverging again before they hit the eyepiece. Okay. So that's basically where we're using reflection to make that focal length longer than the body of the scope had available.
Correct. So one of the things that people it should be understood, and I'm never quite sure if it is, you see all these light paths that intersect each other in air.
Mm-hmm.
Okay. Light is electromagnetic radiation. Unless you're capturing it somewhere, bunch of different beams of light can be traveling through the same space and they do not impact each other in any way. It's not like streams of water that will start intersecting and splashing around.
Okay.
Light does not care unless you are capturing it, measuring it, reflecting it, doing something in that place. If they're just traveling through air, different beams do not impact each other in any way, shape, or form. That's why you can fold this optical pattern itself multiple times.
Okay. So I actually was curious about that because I know there's the whole thing I've heard going back to high school chemistry about light behaves both as a wave and as a particle. In this case, it's more like a wave. And given my background with the nuclear side.